So a very interesting discovery which we have made in the last year or so is that we need to rethink architected materials altogether. To date, we've thought of periodic symmetric architectures as the way forward because they are very stiff and strong. But we've discovered that materials that are actually asymmetric and aperiodic, which is what you find in nature a lot. If you go through literature of self-assembly, you'll find that a lot of these geometries are not periodic, they're not symmetric. And we're able to harness these self-assembly or self-architecture processes to give us very interesting 3D morphologies. And we've been able to show that these 3D morphologies could be as efficient, if not more efficient, than architected materials in the classical sense of symmetric and periodic unit cells. So this self-architecture process, which we have demonstrated in recent years, involves using polymeric emulsions. So you mix the right amounts of polymers in a beaker and you allow them to separate as they normally would, and they form very intricate and interesting 3D morphologies like the one I'm holding in our hand. We've actually been able to compute these morphologies. This is actually something that you would see in one of our materials, of course at smaller scales. These architectures we have shown have very interesting curved surfaces, which leads to very novel and efficient mechanical properties, setting us apart from the classical periodic and beam-based, strut-based architectures. An advantage of this new self-architected fabrication route is that we do not need to rely on advanced fabrication tools like nanoscale 3D printers to realize these materials. But you could, in principle, run this reaction in larger and larger volumes in a beaker, and the process will self-architect itself, removing a lot of the bottlenecks that we're seeing in our field nowadays. So this would really be a game-changing achievement if we can realize it, which would be that we can bypass advanced fabrication tools to make nanomaterials now centimeter scale. The objective would be to be able to show you a nanomaterial and actually hold it in my hand while I'm talking about it. So current bottlenecks in our field of architected materials, the main one I would say is scalable fabrication of these materials. This has been a challenge for the last decade or so. We've been able to show these very novel and interesting properties, but we've only been able to demonstrate it in cubic micron sizes of samples. The idea would be to be able to have these materials at large scales and retain that interesting response, which we really get because we're architecting it at the nanoscale. Potential solution, as I mentioned, so self-architecture, self-assembly processes could provide routes to bypass this. Alternatively, advancements in additive manufacturing could provide ways of speeding up the production, reducing the cost. These are all potential viable solutions, which we hope will give us a way out of this bottleneck. The other aspect is our limited knowledge of these materials. As I mentioned earlier, we understand these materials in these very small set of conditions. So quasi-static, small deformation in most cases. But as I mentioned, we need to understand how these materials would behave if you dropped them or if they were crushed at a higher rate. If we want to apply these materials more broadly in real-world applications, that knowledge needs to be gathered somehow. The other aspect which makes it challenging to work with nano-architected materials in particular is that you're working with very small samples requiring very advanced tools to even visualize our materials. So being able to come up with maybe custom fabrication or testing techniques would maybe allow us to speed up the way we iterate through these materials and understand them as well.